Welcome to AP Chemistry. The units remaining in AP Chemistry, acid-base equilibria, buffer equilibria, precipitate equilibria, and redox equilibria, revolve for the most part in the application of equilibria to reactions in aqueous solution. We start acid-base equilibria with defining what an acid or base is. There are three historical definitions provided above, each one broadening the previous sense. Arrhenius acids produce H+, shorthand for hydronium ion, and Arrhenius bases produce hydroxide. The Bronsted-Lowry definition broadens this so that bases simply accept H+. However, the most sophisticated definition is the Lewis acid-base definition, treating acids as electrophiles, or lovers of negative electric charge in aqueous solution, and bases as nucleophiles, or lovers of positive electric charge in aqueous solution. Mindful of this, in the reaction of hydrofluoric acid with water, water has an available unshared pair that can form a sigma bond with the hydrogen. It is important to note that nucleophiles always begin the reaction either neutral or negatively charged, and will always have an unshared pair available to form a bond. Fluorine, being much more electronegative than oxygen, acts as an electrophile, drawing a pair of electrons more closely to itself. Electrophiles are always neutral or positively charged and will always draw electrons more closely to themselves. It is important to note that in every acid-base reaction, that a conjugate base and a conjugate acid pair will always be produced in reference to the reverse reaction. However, this must be distinguished from the reaction that would occur if a conjugate was purified and then placed into water. In the example provided, ammonium ion generated the conjugate base ammonia. However, this equilibrium reaction is distinctly different from the equilibrium reaction of ammonia with water to produce the conjugate acid ammonium ion. They are related to each other, as we will see, but they are not the same system. Finally, there are several exotic examples of acid-base equilibria. The first is in the absence of water, and the second is in the formation of a complex ion. In either case, again, the nucleophile always begins the reaction with donating an unshared pair, and the electrophile complementarily drawing an unshared pair to itself. Now, depending upon the chemical system, K values will differ widely. If a K value for an acid is greater than 1, the reaction is considered a strong dissociation, and the acid is a strong acid. If a K value is less than 1, the reaction is considered a weak dissociation, and the acid is a weak acid. This trend holds true for bases as well. However, it is important to note that the conjugate of a strong species is not weak. The conjugate of any strong species has no effect, and no reaction with water will occur at all. Only conjugates of weak species, either weak acids or weak base, will also behave weakly. It is for this reason that you are absolutely required to remember all strong acids and all strong bases. The list, however, is extremely small, and they are much easier to remember than a list of all the weak species, which are in the majority. However, a helpful tool to remember the strong acids and strong bases is to connect them with solubility rules, for which you are also required to know. Since they are both based upon strong dissociation, you should connect them accordingly. Nitrates are always soluble, and nitric acid will always strongly dissociate. Group 1 ions are always soluble, and group 1 hydroxides are always strong bases that strongly dissociate. With noted exceptions, chlorides, bromides, and iodides are always soluble, and hydrochloric acid, hydrobromic acid, and hydroiodic acid will always strongly dissociate, being strong acids. With noted exceptions, sulfates are always soluble, and sulfuric acid will always strongly dissociate. These first four rules are most important to commit to memory. From this, we can compare the activity of any species in reference to their K value. Since all of these reactions are reactions in aqueous solution, that is with water, to find the K value of a conjugate base, we simply divide 10 to the negative 14th, the K value for water, by the Ka value. These species can then also be compared. Now, what is it that makes a good nucleophile or a good electrophile? Trends that we will focus upon are the strength of their bonds, the stabilization of the conjugate produced through inductive effects, and through resonance. In the case of comparing HF to HCl to HBr to HI, the bond strength is much more substantial in HF, which lends to less dissociation. I- is the most stable ion produced due to its ion's size. That is, the negative charge is distributed over a larger area. Therefore, of this set, HF is distinctly the weakest acid, and HI the strongest. Next, we can compare acids according to inductive effects, and the resulting stability of the conjugate due to resonance. The polyatomic acids with more oxygen atoms will have greater negative inductive effects, drawing electrons away from the bond of oxygen with hydrogen and thus weakening the bond, tending towards greater dissociation. Additionally, conjugate ions produced are more stable with a larger number of oxygens due to having a greater number of resonance structures that would stabilize the resulting negative charge. Thus, binary molecular compounds with oxygen will form acids in water, and ionic compounds that contain oxides will form bases in water. In the first case, water acts as a nucleophile, donating an electron pair to form a polyatomic acid. In the second case, water acts as an electrophile, accepting an electron pair to form hydroxide. The autoionization of water is central to this narrative of acid-base equilibria in aqueous solution. The equilibrium expression for the autoionization of water is the concentration of hydronium times the concentration of hydroxide. As it happens, if we multiply the equilibrium expression for an acid in water by the equilibrium expression of its conjugate base in water, the result is also equal to the concentration of hydronium times the concentration of hydroxide, or Ka times Kb is equal to Kw. This is what allowed us to find the K value of a conjugate species if we know its initial species that reacts with water. Since the concentration of hydronium is 10 to the negative 7th molar, and the concentration of hydroxide is equal to this in pure water, the Kw value for water is 10 to the negative 14th. Now recall that a K value is constant for a reaction system at a given temperature. A neutral cis solution does not mean the absence of acid or the absence of base, but that the concentration of acid and the concentration of base are in equal amounts. Acidic solutions therefore have a higher concentration of acid to base, and basic solutions have a higher concentration of base to acid. In the next few slides, be sure to carefully understand the models in order to see what is happening in the acidic and basic solutions. Taking the negative log of the concentration of hydronium, symbolized by H+, gives us pH, and taking the negative log of the concentration of hydronium gives us POH. It is important to note that pKw is equal to pH plus POH and is also equal to 14.00 at 25 degrees Celsius. Many weak bases will be referred to in this unit as well, the vast majority having an amine group, a nitrogen with an available electron pair. Conversely to acids, in which negative inductive effects made a better acid, bases will perform better under positive inductive effects, when electrons are drawn towards the electron pair. Stabilization of the conjugate through resonance will always support the parent species. Finally, we end on a note with salts. Any salt can be thought of as being made from the conjugates of bases and the conjugates of acids. This means that salts may have acidic or basic or neither or both properties in competition with one another. The first type of salts provided are conjugates of both strong bases and conjugates of strong acids. These will never have any effect upon the solution. However, take note of the next few examples, for they will indeed have an effect on the solution. Till next time we consider the mysteries of the absolute, Crip.